been waiting way too long. Yeah, I've been down here trying to get it. Yeah, I've been waiting way too long.
All right, this is the video for 4.6, proving triangles are congruent. And so I want you to notice this table that's on page 252. So it summarizes all of the ways that we can justify that triangles are congruent. So there's SSS, SAS, HL, which stands for hypotenuse leg, and that's only for right triangles, ASA, and AAS. So those are the 5 ways that you can prove that 2 triangles are congruent. And you have to be careful to make sure you pay attention to how this is set up. So for example, in SAS, this angle is the one that has to be congruent in both triangles because it's the angle formed by the congruent sides. Whereas in ASA, you see that the angles are outside of the one side. All right, so we're going to prove this. So we have this figure, and we know angle 1 is congruent to angle 2, and 3 is congruent to 4. We're trying to prove that triangle BCE, this triangle, is congruent to triangle DCE. So we're trying to prove that those are congruent. Right now, we only have 2 angles that are congruent in those 2 triangles. So we need to probably work kind of around this in a roundabout way. So I'll go ahead and write my given statement. Okay, so in order to prove that these 2 triangles are congruent, again, I need to either have 3 sides congruent, I need to have a side angle side. Doesn't look like anything's a right angle, so I'm not going to include HL. I need to have an angle side angle or an angle angle side. Again, I already have one angle, so I'm probably going to be using one of these 3. In order to use side angle side, I would need CD to be congruent to CB and CE congruent to CE. Well, CE is already congruent to itself, so I'm probably going to need to use that at some point. So let's go ahead and write that down. CE is congruent to CE, and that is the reflexive property. We're going to probably need that because, again, that side is on both triangles. So now I have an S and I have an A. So I have this S and I have this A. So I probably need CD to be congruent to CB. So how could I say that? Well, if that triangle is congruent to this triangle, then CD would be congruent to CB because those would be corresponding parts. So let's see if I can prove that those 2 triangles are congruent. I know I've kind of really done a lot with the drawing there, but hopefully you see what I'm talking about. So how could I prove that triangle CBA is congruent to triangle CDA? If I can prove this, then I can say this because that would be the corresponding parts. So for CBA, I already know that 1 is congruent to 2 and 3 is congruent to 4. So I have an angle. I also know that CA is congruent to CA, so that's a side and that's reflexive. So I have an angle and I have a side. I need another angle, or another side actually. So I'm going to use the angle 3 and 4, right? So I actually have 2 angles congruent. So now I have angle, side, angle. The first angle is 1 and 2. The side is the reflexive that we just talked about, and the other angle is 3 and 4. So again, that's angle, side, angle. So now I can say that triangle CBA is congruent to triangle CDA, and that is by angle, side, angle. And if that is true, then CB is congruent to CD, and that is because the corresponding parts of congruent triangles are congruent. So if you need to actually write that out, I'll say it again. The corresponding parts of congruent triangles are congruent. And so now, for the proof that I'm really trying to do, I have a side. That's this guy. CE is congruent to CE. I have another side. CB is congruent to CD. And I have the angle in between them. So that is SAS. So triangle BCE is congruent to triangle DCE, and that is by SAS. I know that maybe was kind of confusing, but maybe try to redo that proof on your own and think through how I got that. Okay, so now we're going to look at this proof. JL bisects KLM. What does that mean? That means that I now have two congruent angles. What are the congruent angles? Well, if it's bisecting KLM, then now that angle is congruent to this angle. So in other words, angle KLJ is congruent to angle MLJ, and that's because that's the definition of angle bisector. And I also know that JKL is congruent to JML, so that's this guy is congruent to this guy. So I have two angles congruent. I'm trying to prove that LJM, which is this guy, is congruent to LJK, which is this guy. Now, if I can prove these triangles are congruent, then I can say those angles are congruent by corresponding parts. So my second statement is going to be the definition of angle bisector. And I wrote down that statement up there in blue. Angle KLJ is congruent to angle MLJ. So what do I have here? I have an angle. I have another angle, so I probably need a side. What side can I say is congruent? Well, I can say JL is congruent to itself. Would that help? Okay, so if this is the side, and then I have these two angles, that's angle, angle, side. Is that one of our ways? Yes, it is, right here. So my next statement is going to be that JL is congruent to itself by the reflexive property. So now I can say that these triangles are congruent. So triangle JKL is congruent to, remember to match up the corresponding parts. JK corresponds with JM, so JML, and that is by angle, angle, side. So now I can say my proven statement, angle LJM is congruent to angle LJK, and again, that's because the corresponding parts of congruent triangles are congruent. The last thing here that you need to know is the base angles theorem, which says if two sides of a triangle are congruent, then the angles opposite them are congruent. So what this means is if I have this triangle and those sides are congruent, then these angles that are opposite those sides are also going to be congruent. So in an isosceles triangle, the angles opposite the sides that are congruent will also be congruent. The converse of this theorem is also true. And so the converse would be if the angles opposite the sides of a triangle are congruent, then those sides are congruent. And if a triangle is equilateral, then it is equiangular. And again, the converse of this is also true. So if you have an equilateral triangle, then it's also equiangular. In other words, an equilateral triangle will always have angles that measure 60 degrees because remember the sum of the interior angles is 180 degrees.
I've been waiting way too long. Yeah.